We're going to look at some examples here of differentiation that sort of look similar to what problems that we may have done before, but actually have some subtleties that are going to be important to pay attention to, and we're going to have to use some other techniques for those. All right, so here we're just finding a derivative. We got y equals a function of x, and we might notice we have a power here. And so sometimes students think about some rules that they've memorized for finding derivatives of things with powers. So you might remember a rule for differentiating things like x cubed, right, where you bring down the exponent and subtract 1. Right, so that's a rule that you might think about trying to apply here. You might also think about another rule that you have for differentiating things where you have a constant in the base and a variable in the exponent. So if I had, say, 3 to the x, that's a different differentiation rule. So that derivative is 3 to the x times natural log of 3. We did those before. So sometimes students try to apply one or the other of those rules to this problem. But the big deal here is that the first rule I wrote up here is for when you've got a variable in the base and a constant in the exponent. The second rule is when you've got a constant in the base and your variables in the exponent. And here we have a variable in both the base and the exponent. So we're actually going to need to do something else, and actually neither of those rules is going to be what we use for this problem. So we're going to actually need to do something else. What we're going to use instead is a property of logarithms and then some implicit differentiation. So I'm going to write over here that property of logarithms that we're going to need to use. So this is not a calculus property. This is just a property from algebra about logarithms. It says if I have a logarithm of a power, that I can rewrite that as b times natural log of a. That was in some of the review stuff that we did at the beginning of the semester when we did some review of algebra. So that's not a derivative property, that's just an algebraic property of logarithms. So we're actually going to use that and then some implicit differentiation here. The technique that we're going to use is actually called logarithmic differentiation because we're going to use logarithms to do it. So we're going to go ahead and do that here. I'm going to write that word here, though, so you remember what it's called. Logarithmic differentiation. Okay, so we're going to start by just taking the ln of both sides of our original equation. So I started with y equals x to the x, and if I take the natural log of both sides, both entire sides. So if I had more terms over here, I would need to take the ln of both entire sides. So as long as I'm doing the same thing to both sides of the equation, I'm preserving the equality here. So I took the logarithm of both sides, so we're okay here. But then what I can do is use this property of logarithms on the side that had the x to the x power so that I no longer have variable to a variable power. So I'm going to use that property on this side of the equation. And then I have ln of y equals x times ln of x. All right, so for logarithmic differentiation, the first step that you're going to do is take the natural log of both sides of the equation. And use that property of logarithms. That's the point of doing that. And then secondly, you're going to use implicit differentiation to find what you're after, your dy dx. All right, so we've been using implicit differentiation for a little while now. So we're going to differentiate both sides of the equation with respect to x. Treating y as a function of x. Okay, so on the left side, the derivative of natural log of something is 1 over that something times the derivative of what's inside the logarithm. So I'm differentiating with respect to x, so I'll have times dy dx. That's chain rule. On the other side of the equation, I've got a function of x times another function of x, so I'm going to need product rule on this side of the equation. So the derivative of the first function will be 1 times the second function plus the first function times the derivative of the second function. The derivative of ln of x would just be 1 over x. Okay, at the end here I do have x times 1 over x, which I can simplify to just be 1. So this side of the equation I could just rewrite as ln of x plus 1. And when you use implicit differentiation at the end, you need to solve for dy dx. So I cleaned up this side of the equation. I'm also going to multiply through by y so that I've solved for dy dx. Okay, so on this side, I'll just have dy dx equals. And on the other side of the equation, I'll have y times this whole expression, ln x plus the 1 that I got here from simplifying that. Okay, so at that point, I actually have my derivative. I might notice, though, that the original function was given y completely in terms of x. And so I could rewrite this at the end here, substitute in place of y what y actually is, so that I get my answer completely in terms of x. Okay, so either of these last two things that I have here would be correct answers for the problem. This second one is probably a better answer because it's written completely in terms of x. And again, all I did on that last part there was, from the answer I had before that, I noticed that I have what y equals. And so I replaced what the y is with what the y equaled from the original equation. All right, so the key thing was using logarithmic differentiation. The reason I needed to do that was that my usual differentiation rules didn't apply, but I could use a property of logarithms that helped us do that. So what I noticed at the beginning of the problem that told me logarithmic differentiation was a good strategy to use was that I had variables in both the base and the exponent. So I needed some other strategy for that. Logarithmic differentiation is a good strategy to use. All right, we'll look at one more example like that. Kind of the same process though, but just another example of the same idea.